All right, everyone. So, my name is Viraj, and welcome to the Leetcode post contest discussions by TLE Eliminators. This is going to be the post contest discussion for weekly contest 403. That is the number. Let us start with the problems. I'll go to the first problem first. All right, minimum average of smallest and largest element. So very simple and very easy rated problem. You can see the difficulty also is very easy rated. You will have an array of floating point numbers averages, which is initially empty. Now you are given an array of nums of n integers where n is even. You can repeat the following procedures n by 2 times. You will remove the smallest element, that is the minimum element currently, the largest element, that is the maximum element, and then add min plus max by 2 to the averages. Now you have to return the minimum element in the averages. Now the only problem to take care in this was you have floating point number. So when you actually take the average, you also have to consider the double factor that comes to picture, right? So if you read the test case, it's going to be very self-explanatory. If you look over here, let's say I have this array over here. So what we do is we select the largest and the smallest first. So largest currently I can see is 15 and the smallest is 1. So if I select 15 and 1 and I divide by 2, I get 8, and 8 is the total point, like there's no decimal place in that. So 8 is given in the averages array. Initially it's empty, now it becomes 8. And this 15 and 1 are no longer in this array. Now you select the next largest 13 and the next smallest is 3. Take a summation, divide, again 8 gets added because 13 plus 3 is actually 16. And so on, so on, so on. And look at the last case. You have 7 and 4, add them up, divide, you will get 5.5. So you return 5.5. And the smallest element is actually 5.5, right? So eventually what is happening? I am getting this answer 5.5 from a very simple logic that I am trying to actually take smallest and largest every time and divide them. And when I divide them and I get some number, that number I am trying to store that in an array, and then the minimum of this next array is the given answer. So once I understand the problem, implementation will be very simple, right? So I get this logic that what I'm trying to do. Now how do I actually implement this out? So let's try to tackle each and every point one at a time. So I'll change my page over here. First point is you need every time the smallest and the largest element. So if you need every time the smallest and the largest element in the array, and then you need to pop them out. Once you have the smallest and the largest element, you can say I'm popping them out and they're no longer in my picture of domain. I am going to change my domain to the next smallest and the next largest, right? So that means somehow or the other, the array has to maintain such a structure so that I am able to get the smallest and the largest element in a quick and efficient manner possible. Now, what's the best efficient manner possible which I can think of? I can very simply say that let me sort the array. Sort the array. If I sort the array, then I know the array is going to be in increasing order. And if now the array is in increasing order, so let's say the array is A1, A2, A3, A4, A5 and A6. Let's say there are 6 elements in the array. Now I know very well that A1 is the current smallest and A6 is the largest. Now once I actually do my operations on A1 and A6, I can now jump to A2 and I can jump to A5 and I can say this is my next 2 pair of elements I want to consider. Next I can say jump to A3 and A4, this is the next 2 elements I want to consider. So I can very well imagine that if I have sorted the array, I can run mainly 2 pointers, one pointer as R and one pointer as L, or you can say I and J, whatever, from the front and from the start. Or you can simply say that in a palindrome, how we run variables, I can run a loop from I equals to 0 to I less than n by 2, where n is the size of the array. And I can say that array of I and array of n minus I minus 1, that's its subsequent value from the back, right? From the reverse. If this is I is 0, over here let's say I is 0, then 6 minus 0 minus 1 would be 5. This is this element. So you get a pair 0 and 5. Let's say I is 1, then 6 minus 1 would be actually 4. So you get this pair. So one at a time you will get 2 pairs, one from the start and one from the end, and then you can start taking their averages because you want min plus max by 2. And while doing this, make sure that I am taking double into consideration. So if this is array of I, an array of n minus I plus 1, when I add them up and when I want to divide them, I can maybe divide them by 2.0. That automatically implicitly converts them to a double or floating point type of a number. And then I can push this in an array, in an extra array called averages as I was asked. Or even better, at the end, remember, nobody is asking you print the averages array. Everybody is asking you print the minimum element in the averages array. So why do you need to even create an extra averages array? Ask yourself. Can I not space optimize this as well here and here, and I can say, let me just calculate this average, and then with my answer variable, let's say this is my answer variable, I can just minimize this answer with whatever pops up from here. That is array of I plus array of n minus I minus 1 by 2.0. Make sense? All right. So let us try to actually dry run this on one of the cases, what my approach is. Let's say I'm talking about this array. So you have 1, 9, 8, and then you have 3, 10, and 5. So initially I'll say sort this. So when I sort this, I get 1, 3, 5, 8, 9, and 10. Now I have an answer variable, starts with int max, because I want to minimize. So I can keep my answer equals to a very large number, let's say 1e9, or int max, whatever you want to keep, a very large number in our case. So I take with int max. And then I run a for loop. I say I equals to 0, I is less than n by 2, and I plus plus. Now in this case, remember, n is equal to 6. Now what do I do now? I say calculate the average. Average is going to be array of I plus, as I told you, like this is array of I plus array of n minus I minus 1. And then you can have divide by 2.0 to actually explicitly convert this to decimal type. And then when you actually get this, minimize your answer variable with this average. Now when this actually runs, what happens? You first take 1 and 10 into consideration. 1 plus 10 by 2. This is 5.5. And your answer variable updates to 5.5. Next time you take these two. This is 9 plus 3, that's 12. 12 by 2 is again, it's 6. So this doesn't minimize, it still remains 5.5. And then 5 plus 8, this is actually 13. 13 by 2 is going to give you 6.5, which is not at all your minimized number. So 5.5 still remains same, and your final answer is printed as 5.5. All right, so pretty simple approach. Now let us look at the implementation for this. All right, so as I pictured the code over here, that is the same implementation over here. You take up the size of the nums. Then you have a double minimum in average sort of a variable I created. That's your answer, starts with int max. Sort the array, start off with I less than n by 2. Calculate the average, that's num of I plus num of I minus 1 by 2.0, and minimize this with the average variable. Then you can return this answer. Now, what is the time complexity? Naturally, because you are sorting over here. So sorting is going to take n log n, right? This is actually, you can say O of n log n. And what about your loop over here? This is actually O of n by 2. Now, overall, if you can say this as n by 2, you can say approximately n only, because you don't take into consideration of the constant factors. And now in this, the superseding term is actually n log n. So you can say my time complexity is going to be n log n. Now what about space? Since I'm not using any extra space to actually calculate the answer, so for this piece of code, I'm not considering the space for the vector to store. That's the input nums. If you take that, that's space. Obviously, I'm not ignoring that. But just for this code piece, I'm not using any data structure. So I can say my space to be constant. All right. So this is the end of question 1. Very simple question, very pretty simple standard implementation based question. I think most of you would have been able to do that. If yes, comment in the chat. All right. So comment in the comment section, and let us move on to the next problem. So find the minimum area to cover all the ones. That is part 1. All right, so let us see the problem. You are given a 2D binary array grid. You have to find a rectangle with horizontal and vertical sides with the smallest area, such that all ones in the grid lie inside this rectangle. Now you have to return the minimum possible area of the rectangle. All right, so in this question, typically it's all about visualizing what I want. So over here, you can see that I was given a grid. So it was like 0, 1, 0, 1, 0, 1. And then they said they have marked the pink area for you. The whole pink area is the smallest area that is encapsulating all the ones. There are 3 ones in this, and it encapsulates all the ones. And remember, I want a rectangle, as in I can even form a square because I know square is also a rectangle, but I want some sort of a structure that looks like a rectangle only. I cannot pop out maybe a trapezium or maybe a triangle sort of a area from this. I want a rectangle and I want the minimum area possible. So that's our next topic. Let's say I am talking about this one over here. Now, would I actually want to encapsulate the whole area? No, I know only this small box over here is encapsulating the single one that is in my capacity. So if it's encapsulating the single one that is in my capacity, do I need to check further of how would I actually come up with the smallest area further? I know that only encapsulating this box is giving me the correct approach. It's giving me the correct answer. So when I visualize this diagram, what pops in my mind at the first? Obviously, there is the rectangle. So I have some ones and zeros. Let's not comment on what they are. Let's say I have taken up them as random numbers. Let's say A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Alright, so I have a 4x4 grid over here and I have drawn some random variables. So imagine that either they are 1 or they are 0. Not a problem with me. Now, I am trying to figure out a rectangle, right? I'm trying to, let's say the smallest rectangle I figure out is this. Let's say that's the case. Or let's say the smallest rectangle I figure out is this. The whole argument of figuring out that I would have the smallest rectangle starts off with a very simple point that first of all, this rectangle should encapsulate all the ones. So if I say that this is my correct rectangle, that's the red area, then all these variables are 0. All these variables have to be 0. If any of them is 1, then I know this rectangle is not encapsulating all the ones in it. So now when I got this area that this all this has zeros over here, then I can also argue over here that if this was the smallest area possible, or if this was one of the rectangles possible, then you can also say this is also rectangle possible. If condition 1 is to encapsulate all the ones, then all ones, then tell me if I say that all the ones are lying somewhere over here only. Let's say this is a 1, this is a 1, this is a 0, this is a 0, this is a 1, this is a 0. So you have 3 ones over here, right? This is 1, this is 1, this is 1. Now even the red rectangle and the green rectangle, both of them are encapsulating all the ones. So first condition fulfills, but I again have to minimize. If I have to minimize, I somehow need to imagine this like this. Let's say this was a rectangle. You somehow have to place perfectly at a point of creation of this rectangle where area is minimum. And how do I come up with that? I can very well see that if I want to chop off the minimum area possible without hampering the case of encapsulating all the ones, what I can do, I'll draw this with the red pen only. I can find from the top the first row where I find a 1. From the bottom, I can find the first row where I find a 1. From the left, I will find the first column where I find a 1 column. This is row. This is row. And from the right, I will find my first column where I have 1. So when I find that, what happens? Let's say you from the top find the first row. This is the first row where you have the 1. From the bottom, first row. This is the row where you have the 1. From the left, first column. Not this, but this is actually the point. And from the right, this is the point. Now let me encapsulate them. Look over here. Let's say this point, I'll take some other pen actually, which will pop up very quickly. Let's say yellow, yeah. This point, this point, this point, and this point. Now you have 4 intersections which created a rectangle for you. Yes, and when this happened, you made sure that all the ones got encapsulated in them. How? Because from the top, you were skipping the rows till you found the first row where you had a 1. So from the top, all the ones have kind of come into picture. When you say from the bottom, you were skipping the rows till you were not finding a 1, but you stopped at a row where you found a 1. So from the bottom, you have also excluded that non-given area for you, which was not required. From the top, you have excluded that area which was not at all required. From the left, similarly, you have excluded that area that was not required. And from the right also, you have excluded that area that was not required. So now you have the best possible area left, which is following your first condition. And if it is following your first condition and you have made sure that you have excluded all the bad area, all the area that was futile to you, then are you not sure that this is going to have the smallest area? Are you not sure that this is going to have your smallest area? Yes, I am sure. Make sense? So this is what our whole point and approach is going to be. So once I've understood this case, you can actually dry run some part in this. So I'll show you a test case on this. Let's say I'll talk about this test case only, right? All right, maybe this test case isn't not worth it. Let's talk about some other grid. Maybe let's have 1, 0, 0, 1, 1, 0, 0, 1, 0. Now in this, from the top, find the first row. From the bottom, find the first row. From the left, find the first column. And from the right, find the first column. Take this area. You have 3 cross 2. Yes, and can you not say that this is actually the correct smallest area of rectangle which actually captures all your ones? Yes, it does. So I think I'm pretty clear on my explanation part for this. If you have any doubts, you can definitely ask in the comment section. But again, I think if you draw some cases of your own, you will understand why my argument stands over here. Now remember, I am not trying to find the rectangle, but rather its area. So if I have to find the area, what I can say my final approach is going to be, let's say like in this grid actually, you can say that from the top, like I would have something as 0, 0, and then I would be extending to the other length. So I can say that whatever is the bottom index I find minus whatever is the top index plus 1. This is actually going to give me the length. Like this is actually going to give me the length, or not rather length, I should say. This is actually going to give me the breadth of the rectangle. And similarly, if I have the right, I have the left, and then I do plus 1 in that, it gives me the length of the, length of the rectangle. Yep. Now, if you have the length, if you have the breadth, and you want to find the area, multiply them. Very simple formula, A into B. That's the area of the rectangle. Yes. So once this approach is clear, I get the implementation and I can start off with, I can show you the code part and you will understand this very quickly. All right. So as expected, I have a top, bottom, left, right. Initially, everything is -1. I then find out the n and m, n cross m. It's a matrix. So I want the n and m. So it's grid.size and grid of 0.size. Now I'll start a loop. This loop will help me find the top and bottom. So I run my logic in the rows first, 0 to n, then in the column 0 to m, that's j. Then if I and j is 1, if grid of I of j is 1, that means this is a 1 I found. Now, if this is the one I found, I want top to become I, that's the first row, if it is not negative. So if it's -1, you make it I. And the next time top is not -1 at anymore, so top never gets updated. But look over here, bottom is always getting updated. Bottom is always becoming I. So let's say you find some row at the top which has 1, then bottom gets updated with I. So on, so on, so on. And this keeps happening till you actually come up with the last row where this was updated, which had a 1. So you can obviously do this in 2 for loops. Maybe you create one for loop that iterates from the top to the bottom, and then one for loop which creates from the bottom to the top, and then initialize top and bottom in its separate manner, and then break wherever you want. But I have done this in a single loop. So it's single 2 loops actually. That's simply a implementation detail. If you want, you can actually picture this out this way, or if you don't want, that's all right. Use your 2 loops, you're free to go. There's no problem on constraints. Just keep in mind you're not exceeding the time limit. All right, target is to find the top. That's the first row from the top which has a 1, and the first row from the bottom which has a 1. Now, similar approach for finding the left and right. Now, this time, look, I'm running in columns first. That's from 0 to m, and then in rows. Same approach. Find the left. If it's -1, then initialize, and then never initialize it back. And right always gets updated. So this gives me the leftmost column and the rightmost column which has a 1. Now, area is going to be right minus left plus 1 into bottom minus top plus 1. And then I finally return the area. This gives me a right answer. So what about time over here? Naturally, you are using 2 for loops over here, right? And both of them are in n cross m order. So you can say time is going to be n cross m. This is also in n cross m. And this is also in n cross m. So obviously, I have an overall complexity of n cross m only for the time. So I can say TC, that's time complexity, is O of n cross m. Now what about space? Naturally, I'm not using any extra space to store my answer, so I can say this is constant. All right, now if I actually run this out for you, so I think, yeah, gets accepted. So this definitely works, and this is giving me the correct solution. All right, so just take away from the problem is implementation. Up till here, both 1 and 2 problems both have been implementation based problems only. So if you get the implementation part, understand like the problem of what the picture, yeah, this also gets accepted obviously. If you get the implementation part, then you're good to go in this problem, because thinking part was not a lot. All right, now let us move on to the third problem. Maximum total cost of alternating subarrays. Now, first of all, I also got confused in this part. All right, so you have to understand what the cost is about. I had maybe like a 5-minute thinking of what this actually is asking, because I was getting a confusion at small part. I mean, maybe you were not, maybe you were. I just need to clear this up for you. So let's begin with the problem. You have an integer array nums with length n, and the cost of subarray is given as cost of LR is nums of L minus nums of L plus 1 plus ... plus nums of R into -1 R minus L. So this actually, like this cost over here actually means it's an alternating subarray, right? You can see this in the name also. You have, let's say for some array, I'll remove this. Let's say for some subarray A1, A2, A3, A4, A5. Let's say you have this array and you've tried to ask me what is the cost. So I will say the cost is going to be the first element is positive, next is negative, positive, negative, positive, and then add this up. So you will say A1 minus A2 plus A3 minus A4 plus A5. This is actually the cost. That means when you actually take up an array, you will have to place plus minus alternate manner, starting off with the plus, and when you add it up, it is going to give you a cost. Now, where do I get this approach? Where do I get this idea? As in explanation, by reading this part. Look over here. Every number is getting multiplied with negative power to R minus L. All right. That means you have a total negative power that is getting multiplied, and it's starting off with a plus symbol, because you can see over here nums of L is positive, then it's negative. And this continues till the pattern till you reach the end. So this is where I finally understood that yes, the cost is something that starts off with a plus, minus, so on, till I reach the end of whatever array I choose, and this is actually going to be the cost of L comma R for that subarray. All right. So I hope this has become very clear. All right. So now what is asked? Your task is to split nums into subarrays such that the total cost of subarrays is maximized, ensuring each element belongs to exactly one subarray. Formally, if nums is split into k subarrays where k is greater than 1 at indices I1, I2, so on till ik minus 1, then the total cost is going to be something that looks like this. All right. That is actually the argument. It is going to look something like this. Now return an integer denoting the maximum total cost of the subarrays after splitting the array optimally. All right. So you have to split the array. You have to split the array in such an order such that you are able to find the maximum. You are able to find the cost. And when you net sum every cost, you want that cost to be maximized. All right. All right. So let's say these are some explanations given to you. Let's say you take up this array. This nums over here. Then over here, what they have said is you can take divided into two parts from the middle. This is 1, -1. So now 1, -1 gets converted to, this is +1. Then this would be negative of -1. That's +1 again. So this is 2. This also has a sum 2. Add them up. You have a 4, and 4 is the maximum possible. All right. All right. Good enough. So now let us try to actually come up with some small observation pieces in this part. All right. So that I can try to build your approach, and I'll tell you why I think that this approach works and this doesn't approach. All right. So just a straight of a bad thing comes in your mind is greedy. What if I can have sort of a greedy approach? You're obviously trying to maximize the cost. So maybe you can come up with a greedy solution to take such subarrays where you maximize your cost. All right. So let us try to imagine that part. First of all, I'll come up with a very small argument. Let's say a number is positive. If a number is singularly positive, then what would be the best case? Naturally, the best case would be you take this number as it is. Is there any limit to how many subarrays you can form? No. Remember, you don't have a limit on how many subarrays can you form. So a single number can also form a subarray. So if you have a positive number and you want to maximize your cost, what if you take this positive number as it is? Now, if you take this positive number as it is, you know that your subarray's cost is starting from a plus and then negative, then a plus, then a negative. So if this number is positive, it gets fit right over here. And it plus sign with a plus sign obviously remains a plus sign. So don't you get this number's best value positive out of yourself? And you get this added to your answer. Yes. So greedily, don't you think this is best? Yes, it seems correct, because if I have a positive number, I would want my ideal case to extract that positive value and take that into my answer for making my answer go as large as possible. So greedily, this makes sense. So we are all done with the positive case. But what is the problem now? You also have negative numbers in your array. Let's say there is a negative number. Let's say there's a negative number in an array. Now, ideally, because there is a negative number in an array, if you take this number as it is, then the first number has to be a positive symbol. Will go with a positive symbol. A positive with a negative still keeps this negative. So you are trying to, when you add this to your answer, you will decrease your sum. Do you want that? Ideally, I don't want that. So what should be the case? What should be the case? Can I not say that if I have a negative over here, then I can pair this negative with a number that comes behind it? Why? Because by the same logic of trying to keep use of maximum case of the value, will I not wish that I would have the power to convert this negative to a positive? And I can only do that if I keep this number to be the second number in a subarray. So I can say that any number that stands previously to it, let's say there's a number over here, let's say this number is A, then let me take this subarray now. That is the previous number and this negative number together as a subarray of size 2. What will happen over here? Now this A will come up with a plus sign, obviously, but this negative will now become a negative, this becomes a positive. So now you have the power to use this value's absolute term added to your answer. And this helps you maximize your answer even further. All right. So now when I have told you this final approach, I think over till that part, you must have also been able to come. All right. Greedily, you must have also been able to think that, let me say, when I have a positive, I will actually take this value as it is. And if I have a negative, then what I can say is I can take this value, absolute value, along with whatever was coming behind it. And then maybe I can have a sort of a I pointer. Maybe I can shift it 2 times or maybe 1 time accordingly. Like you can come up with that approach if you are able to think up to this part. But what the argument over here is, think like this. Can you for sure say that this greedy approach is going to work? No. Why? I'll tell you a case. Let's say you took A over here, right? And you have a negative number over here. So you said that converting this negative was giving me an ideal case of converting this to a positive. I converted this to a positive number. All right, and I got a positive value over here, and this was A as it is. But what if I told you that converting this number from a negative to positive and taking the previous number into consideration was not the correct case, and maybe you could have dropped this number as it is and kept its value and rather moved on to the next value? You have both the possibilities, right? You could have said that I can have taken this negative value as it is as a single subarray, or I could have taken this in a double subarray. Both the answers have to be taken into picture. I can never say this for sure that converting this negative value to a positive by taking its previous number also into consideration and creating a subarray of 2 would be the best optimum approach. Because what can happen is later on some number can come which is going to hamper everything for you. All right. If you don't believe me, you can actually try to code this part out and you will get a very good test case. I'll actually drop some good test case about this in the comment section to actually prove my greedy thing to be wrong and why I think this is not going to work. So because of this, I have to make sure that I take both the options into consideration. What are you going to be 2 options? Option 1, if you are standing at the ith index, and you have nums of I with you, then one case can be take this nums of I as it is as a singular piece of array. So singular piece of subarray. If you do that, whatever answer is the maximum stored till I minus 1th index, you just add to that value. What is the option 2? Option 2 is I argue that no, I want to make this nums of I, since this is a negative number, I want to convert this to a positive number. In option 1, I have not converted it because I've taken it as it is. If I've taken it as it is, it remains negative only. But option 2 is I want to make it a positive. Because I want to make it a positive, I will have to take whatever is the maximum answer till I minus 2th index plus the previous number, that is nums of I minus 1 plus negative 1 into nums of I. Negative 1 into nums of I. This is actually the conversion of this number, nums of I, from positive to negative. These are the two options you would have. Now, because I'm talking about two options, very simply, this gives you an idea. I have a DP problem or a DP solution in this problem. All right, I can start, like I can create a 1D DP, right? 1D DP where DP of I stores max till ith index. All right, ith index. Or if I have a 1 based indexing, then I can say DP of I stores max till I minus 1th index. All right. Like this argument is not important. Otherwise, you understand the 1D DP concept in this part. So 1D DP where DP of I stores maximum till the ith index. What is going to be the transition states? Transition states can be DP of I is equal to DP of I minus 1 plus nums of I. This is nums of I. And what is this option? This option is if you take nums of I as a singular array, DP of I minus 2 plus nums of I minus, you can say over here, nums of I minus 1 plus minus 1 into nums of I. This is actually you converting the nums of I number into from a negative to a positive. And these two cases are if nums of I is negative. And the third case is going to be simply DP of I minus 1 plus nums of I. This is actually your case when nums of I is positive. So you can obviously club these three cases because you can see very well over here that you have only positive and negative. Like overall, you have basically I've written three states separately to show you negative and positive case, but either way, it's working in a similar manner. So you can convert them into a single statement finally for positive and negative both, and you can just remove this state, and this handles your positive also, and this is obviously both for negative. So either way, you can just take both into consideration, not even bothering about thinking where you want negative, where you want positive. All right, and this is going to give you the right answer. Now let us try to do a dry run on some case so you will understand this. Let's say this array. So you have 1, negative 2, 3, and 4. So I start off with the base case. Obviously, base case is DP of you can say 1, or DP of 1 is actually 1. Because that's a single number and you have to take it directly only, so you take it with a positive symbol, right? Or whatever symbol this has, like it's at positive, negative, it doesn't matter. You just make it to be nums of 0 or 1. Now you can start your loop for I equals to 1, I is less than, you can say n, and I plus plus, right? Now what happens? I have two options obviously, so I'll make this option 1. Option 1 is take DP of I minus 1 and just add nums of I to it, considering that nums of I was a singular subarray. Option 2 is to handle the negative to positive case. DP of I minus 2 plus nums of I minus 1 plus nums of, this is negative 1 into nums of I. All right, and then DP of I becomes whatever is the max of option 1 comma option 2. And then you can at the end of your final loop, come out of this loop and you can return DP of n, because that is going to store you the till the n minus 1th index your correct answer. All right. Now, what is the takeaway from the problem? Like at a very immediate glance, it won't seem that this is DP, right? It might seem that greedy might work, but greedy will not work because of this case. I told you, you have to take into picture both the options. What if you did not take the idea of making the current nums of I in a which was a negative number to convert to a positive number? What if you did not do that? You can always do that, agreed, and it would have been given you a good answer, but you're not sure that can give you the maximum answer, right? What if dropping that currently and then maybe taking it later with some other subarray would have been a better case? So you have to take that option into consideration. Because you're diverting into two options, you cannot apply a direct greedy approach. You will have to keep states, and once you understand the states, this transition is very easy to write. All right. So I would recommend do practice 1D DP in this part, right? This is kind of like a house robber problem or something sort of that, to understand that why I need two sorts of options. Why this current approach of taking greedily negative is not, like, positive was very clear. If positive is there, just take it as single number, we're good to go. But if a negative popped into picture, I would have to take two options. I cannot just simply say out of the straight bat that I take this number and the previous number and convert it to negative. That's not going to be the most optimum case always. That's why I have to keep a two option set or a DP approach. All right. Now, once this is clear, I can actually jump to the code part to actually show you. Yep, code over here. You have, I'll take the size of the nums, that is n. Create a vector n plus 1, starts with 0. DP of 1 is nums of 0. Start with loop. Option 1 is DP of I plus nums of I. Option 2 is DP of I minus 1 plus nums of I minus 1 plus negative 1 into nums of I. This is option 2, this is option 1. Take the maximum and store that in I plus 1, and then you can return DP of n over here. All right, so I think I also misplaced some states over here. This is actually going to be I, this is going to be I minus 1, and this is going to be I plus 1, right? Just an indexing based sort of a mistake you can actually take into consideration. Be careful of that so that you get the correct answer, you don't get any segmentation error. All right, now what is the time complexity? Now it's really the time complexity is turning out to be n cross m, not n cross m, my bad. Simply O of n, because you are running a simple loop over here that is in n order, correct? And then what about the space? Now I'm using an extra data structure of the size n to actually calculate my answer. So I can say my space is actually the size of the DP, that is n size. Now this definitely runs, gives me an accepted solution. So that's the correct part. And I am good to go. Let us end our third solution over here. All right, so we have the last and the final problem. Find the minimum area to cover all the ones too. Now, obviously, this is like an extension of the first problem, right? This is the first problem. So you kind of have to imagine this into very simple picture that somehow or the other, the logic of 1 is getting extended to the logic of 2. Right? That's a very, very clear intuition, right? When you're solving the contest. Now, otherwise, I don't want to recommend this in normal problems, but because there's a contest, you can understand that, yeah, same problem names 1 and 2. That means somehow or the other, this idea is getting extended to this idea, right? So let us read the problem. You are given in 2D binary array grid, similarly like the first problem only. Let me keep this next to this only. You need to find 3 non-overlapping rectangles having non-zero areas with horizontal and vertical side, such that all the ones in the grid lie inside these rectangles, and you have to return the minimum possible sum of the area of these rectangles. Now you have to note that the rectangles are not allowed to touch. So they are allowed to touch, as in they can touch with their boundaries, they cannot overlap, right? Over here you can see, let's say the rectangle purple, blue, yellow, they touch, right? They have a common boundary, but they don't overlap. All right. Now, why am I saying is this is an extension of the first problem is, over here in the first problem, you had to find only one rectangle. Finding that one rectangle, our logic was very clear. Find the top row, bottom row, as we did, like see over here. Find the top row, bottom row, left column, right column, and then get the area. Over here also, somehow or the other, you have to do that part only. But the problem is you need to find 3 separate rectangles. That means you cannot take this into one single rectangle. So when I actually propagate the idea to you, you will understand that this is a very easy problem. This was all about visualization. If I tell you somehow that I am able to figure out all the possibilities of where these 3 rectangles can be in the main grid, then what I can do is I can find the minimum area for each and every section separately by using the first function call. I can make this problem only itself as a function call, and I can declare that as a section. Now, what do I mean by this? Let me be more clear on this part. Let me drop. Let's say your grid looks like this. All right. Now let us discuss the possibilities. I think I have 6 pages. No, I don't have 6 pages. So let me create actually 6 pages. 1, 2, 3, 4. I think I have 6 pages now. Now I'll give you the possibilities. One possibility is that your rectangle 1, you have 3 rectangles, right? 1, 2, 3. So I don't want to number them, right? You can take any numbering, not a problem. One rectangle is in this section, one rectangle is in this section, and one rectangle is in this section. This is one possibility. Imagine. It can happen, right? You can have some rectangle that is placed over here that covers all the ones, then maybe some over here which has some distributed ones, and then maybe some small rectangle over here that is distributed ones. So can I not draw such sort of bifurcation where this is segment 1, these are the 2 segments? I'll tell you one more. Similar, can I not draw a segment like this? Similarly, can I not draw a segment like this? Similarly, can I not draw a segment like this? Now, next, can I not draw a segment like this? And can I not draw a segment like this? I think I've covered all the cases. Yes, imagine I only have these many number of possible cases of the occurrence of these 3 rectangles. Wherever you find these 3 rectangles encapsulating all the ones, don't you think that they will fall in any of the 6 cases? Can you think any other case? Let's actually look at the case. Let's talk about this case. Tell me which is this case. This case is actually falling at this. Correct? Can you not see that this rectangle over here, purple, will fall in this part? The small blue falls in this part, and then the yellow falls in this part. So you divided your main grid into 3 columns which had their 3 separate rectangles. So case covered. What about this? Can you not see that this falls in the first case I told you? Look at the first case. You have some part that falls above, totally covering everything, then divided by 2, the middle part, divided by half segment. You have something that covers in this segment and something that covers in this segment. That's all. So if I imagine that yes, I have only and only these 6 possibilities of covering this sort of a rectangle, then can I not say, the possibility of covering these 3 rectangles in a general area, then can I not say that now I have a very sorted function with me. This function runs in n cross m complexity, and look over here. Your time complexity can exceed to a very good limit because n and m both are in 30. So imagine this part. You have a function with you that runs in n cross m grid, n cross m complexity, and then I define my area. So I say, I will give you this segment, I will divide this and I will give you this. Let me draw this with a different pen. Let's say I have a green pen over here. I give you this segment, and in this segment, find me the smallest area which has covering all the ones in this specific area. Now, don't you think this is a question of one only? In the first question, imagine if this was actually your grid only. This green part was actually your grid. Then in this grid, your question would have been, find the smallest area of a rectangle which covers all the ones. So would you have not called this function for this segment? Yes, you would have. Similarly, I can say call your function for this segment and call your function for this segment. So can I not say that total now for the first, this is like the first possibility. In this first possibility, you will have covered all the possibilities of forming the rectangles. You can have this as a separate loop, create this for your one possibility, and then copy paste your code by changing some small parts of the area to for a second possibility, that you could have had the main rectangle over here and then some 2 rectangles at this part, maybe some small rectangle over here, then big rectangle at this part, maybe some small rectangle over here, big rectangle at this part, and then maybe some big rectangle over here, and obviously the last case I showed you, 3 rectangles at this region. So I can have 6 separate logics to handle 6 separate cases. And when I handle these 6 separate cases, in that every case can have the function calling to actually calculate for every segment the smallest area possible by the first question itself. So this is where my whole idea pictures, right? Why? You will ask me, why did I think of this? I thought of this because of very simple logic that, first of all, problem is an extension. So somehow it makes very sense that first thing is going to get used. If I have to use the first thing, it has an extension. So that is where I started thinking. I started asking myself, I know that I'm trying to place 3 rectangles. Now, if this question would have been, place k rectangles, 4 rectangles, 5 rectangles. Maybe I could have not done that. But because there were only 3 rectangles, I took my pen and paper, sat down, made some cases, and I started seeing something. I saw that I am not going with outside the boundaries of these cases. I can only form my rectangles in such a case where I'm able to actually divide them in 6 bifurcations, 6 possibility of bifurcations. Once I visualized that part, I was able to very well figure out that if I am able to get the segment, then in that section of segment, I can call that function and define that in this segment, find the best area. And that function call is going to help me create this problem also that somehow or the other, the first intuition and the logic got extended to the second problem. So my mind when I was doing this problem was running through this part, somehow use the first logic to the second logic, and then somehow try to build up cases where you can actually identify how many possibilities are there. I asked myself, is there a lot of possibilities? When I asked myself, I tried to answer myself. When I tried to answer myself, I got the logic. All right, so like this is the whole idea, right? Again, I don't expect otherwise that this very well pops up in the part, but visualization and explanation goes parallelly. So if you are able to visualize this part, kudos. If you're not, please sit with your pen and paper and you will realize that what I'm saying is actually right. And it makes kind of sense that I cannot exceed the possibilities, the 6 specific possibilities of bifurcation of areas I showed you. All right. Now, once this is clear, code part is going to be very, very simple. All right. So let us actually jump to the code part. So I have the first logic over here with you. I'll show you what I've done. See the second logic. In the second logic, also I've called the same function. I've just changed some small parameters. I'll show you. This is the same function to calculate the minimum area. Now let's come to this part. The first case, divided like the first, second, and third. What do? I, j, obviously. Now I have m grid size, n grid size. Or I can actually take this. Now I have the answer. Initially, because I want the minimum area, so I start off with a very large value. That's 1e9. And then I have rectangle 1, rectangle 2, and rectangle 3. Now I start off with a loop from 0 to m. So this is first in the rows. When I have first in the rows, I'll say simply that first rectangle is placed from grid. Obviously, it's in the grid. From where to where? It's between the 0th row to the ith row. And it extends from 0th column to the last column. From this segment, find the first best rectangle. So you call this function, that's the same function. See the same function. It's the same function. Top, left, bottom. I have just not changed anything. What I've changed over here is I've taken 4 extra variables. Because I know that I am trying to find the minimum area, but in a seluded segment. That segment is it's like bounded by some 4 variables. That 4 variables is where do you start off from? Where do you end from in the I direction? Where do you start off from in the column? And where do you end in the column? Only there you will run the for loops. So initially you can see my for loops were from 0 to n, 0 to m, 0 to n, 0 to m, but now they're not. They're from sti to eni, that is start row to end row, start column to end column. Find the top and bottom. Similarly, then start column to end column, start row to end column, end row, find the left and right, and then return your area. That is right minus left plus 1 into bottom minus top plus 1. All right. So I do this and I find first the first part. And then for the second, now this line over here, I'll try to picture this over here. I'll draw this again. Let's say like we are trying to like dynamically find the area, right? So I know the bifurcation is going to look something like this, but this bifurcation can change, right? First bifurcation can be this line of bifurcation can move down. It can be over here, it can be over here, it can be over here. And similarly, for one bifurcation, this line of bifurcation can also move to the left. It can be over here, 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 here. That is where the loops. So if you imagine this, you will get this part. So what I've done over here is, one loop is obviously running, which has the rows. So it starts with 0 to i, and then I increases. So sometime your bifurcation is this, then next time is to this, next time is this, next time is this. Then what about this bifurcation? This is also increasing, right, from the left to right. So how can I do that? Maintain a loop, 0 to n. So the second rectangle would be the minimum area you find in the grid from the I plus 1 column to the end, but from the 0 to the j. Sorry, from the I plus 1 row to the end row, but from the 0 to the j column. And then the third rectangle has to be kept from I plus 1 to m minus 1. That's true from the top to bottom, but it starts after j, that is j plus 1, and goes till n minus 1. And then whatever is the minimum of 1, 2, and 3, it gets stored in the sum total as minimum of answer. Correct? Now, once you have understand this part, realize the complexity of this. You have n cross m cross, the function call is again n cross m. So you have a n square m square complexity, which is for 30, you can say this is going to be 3 power 4. You can say this is 3 power 4 into you have 10. This was like 10 and then 10 power 4. So you can say this is going to be 10 power 4. Right? 30 into, that was like 30 to the power 4, simply 30 to the power 4. And 30 to the power 4 is obviously going to give you something that looks like this is going to be 81 into this is going to be 10 power 4, which is actually simply, you can say, in a 10 power 5 order. 8 into 10 power 5 order, something like approximately, right? Approximately 8 into 10 power 5 order. So I have done this to actually find one segment, right? One structure of bifurcation of areas of the three rectangles. I am going to do this for this case, for this case, Control Z, for this case, for this case, and for this case. And once I have done this for all the 6 cases, I can return my final answer. All right. So now this is not going to be a very big deal if you understand the first piece of code. Like obviously this code is going to be attached in the video link, so you will find the code itself. But the whole argument, like this part, once you get how am I picturing this part, then this is all implementation, right? If you want to implement this, in this case, what will happen? You will first go in your columns first. So from 0 to n is defined as like n I took as columns. So you will go in columns first, find the first rectangle, then in the rows, try to find the 2 and the 3. So this is the first, extends from here, and then the 2 and 3, and then take the minimum. Similarly over here, I've started from the back type because I want from the back one. Over here I've started from the bottom. Over here I've only kept from the top, and over here I've only kept from the bottom, right? Over here you can see 1, 2, 3, all three are getting found out in the same for loop inside one. Alright, so this is like just implementation. Once I tell you that you have to calculate the minimum answer for all 6 possibilities, each possibility can be imagined as an implementation based question. And then somehow or the other, it's totally up to you how you run the for loops, how you calculate your pointers. Just the approach is get the idea, get the bifurcation, and only find that bifurcated area's minimum area rectangle, and find this for 3 rectangles, get the total answer. All right. So hence extension to the first problem, you can say. So as explained, the time complexity, what is the time complexity now? Time complexity over here is going to be O of n into m into n into m, which is actually equal to something like this. What about space? Am I using any extra space? No, I'm not using any extra space besides whatever is the space that could have been there for the grid. That means I have a space of constant. All right, good to go. All right, so I think this is what finally clears up our idea. We have covered all the problems, and that is all good to go. So I think this contest was overall just a visualization and implementation based problem, right? Along with this DP problem, right? So yeah, that brings us to the end of our PCD for the Leetcode Weekly 403. I hope you liked the video. Thank you so much for watching.